to the organic chemicals in general, like this is a chemical process where at least two consecutive reactions can be performed in a single crop. So since I'm telling this consecutive reaction, that means the second reaction will start after I started forming the first reaction together. So here in this work I have used ammonia borane hydrolysis and nitroarene reduction to aniline derivatives for the tandem reaction. So you can ask why nitrogen reduction or why aniline derivative? Because these aniline derivatives are playing key role in synthesis of many intermediates of pyrogen, dyes, pigments, and applications. According to the verified market research, hello,
Jero,
yeah,
lock your door actually. I think there are a lot of voice.
yeah, my door is locked already.
8 seconds, bro. Dino, bro. Continue, bro.
Continue.
Continue. It's fine.
Yeah. So according to verified market research, so that in 2020, the total amount of aniline derivative was produced throughout the global is 7.3 million tons, and it will be increased to 11.82 million tons in 2028 with a compound annual growth rate 4.93%. So this huge amount of aniline derivatives are synthesizing by using hydrogen as nitrates with some reducing agents. So reducing agents means the hydrogen we have to use there, and for that people are using different alcohols like ethanol, IPA, and all those things. So but the problem in this PVC is that the reaction rate is very slow and this selectivity also very less there. And to conduct this hydrogenation reaction, we have to use high temperature as well as high pressure. So that we need a very yeah. So a useful such suitable hydrogen source is very demanding to conduct this reaction. So that's why the recent year, Ammonia Borane got very interest in the research community as a hydrogen source because because of its lightweight and high hydrogen content. It is containing 19.6% of hydrogen in the sample, and it is highly soluble in water and highly stable. And most importantly, it can release the hydrogen at ambient condition. So, ambient condition in products of catalyst. Uh, these nanomaterials are good tandem catalyst because it has a high surface area to volume ratio and it is able to conduct in many reactions on its surface. So, when we're talking about catalyst, we cannot just ignore the palladium nanoparticles because it's heavily used in the catalyst industry. But palladium nanoparticles are not like it is not
Bro,
stable. Hello, hello, yeah. Hello.
are you changing the slides or not? Just this
No, 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 no.
slide
I'm
only.
not changing. I'm not changing.
Okay, okay, continue.
Actually, two logger system were side by side. That's the reason this echo is coming. Can you we need to disconnect one logger system.
Yeah, yeah. Only one system only login.
Okay, okay. I
In
think the two log
mobile also it is on. That's why
that's the two logger systems should not be side by side. That's the reason this echo is coming.
once again. But without mobile connection, I cannot use this Telegram, right?
It's okay. Continue, then, bro. Maybe some other issue there. Maybe I think we'll see later that one.
Okay. So yeah. So this palladium, where palladium nanoparticles are not stable because it of its high surface energy. And because of its high surface energy, it will always try to aggregate each other, and the bulk material will form, and it will be unstable. So to immobilize these palladium nanoparticles, people are using various supporting material, support materials like metal oxides, product materials, and metal organic chemicals, and so on. So the problem there is if we use those support materials, then we have to use some of the material up during the washing period. But if we use the Fe3O4, then we don't have to face that problem because Fe3O4 is a magnetic metal. We all know that. And after the synthesizing and washing the catalyst, if we just put a strong magnet outside the reaction container, we can collect the entire catalyst. So we don't have to waste. There will be no problem with the wasting of the catalyst. So that is why I have chosen this Fe3O4 as a support material, and palladium is the active catalyst here. And this is a core cell material I have prepared in this work. So what is core cell nanostructure? That means that there will be one core which is support material here, and the cell is the palladium. Cell will be the overall core material. Support material. So here core is FeCO4 and palladium is the cell. So it will be uniform layer of palladium over the FeCO4, that is core cell structure. Here in this core cell nanostructure in figure, you can see that core cell I have written inside that circle, and outside one more circle. It will be like that structure. But FeCO4 here is octahedral, so the core will be, the cell will be also over this octahedral structure only. So I have prepared this Fe3O4 Pd core cell nanoparticles. So I have synthesized this core cell nanostructure by using a complete solid state approach. But generally, people are using this synthesizing these core cell nanoparticles by using wet chemical synthesis process. The problem there is that we have used huge amount of organic solvents as well as strong reducing agents, and we have to use several times of washing to eliminate the unwanted reagent from the desired catalyst. So this is a time-consuming process. To avoid all this process, I have used this solid state synthesis process. So what I have done is Fe3O4 and palladium TeR I have mixed in a mortar pestle and then grinded for 30 minutes to get a homogeneous mixture of palladium TeR over Fe3O4. And then I have heated that solid mixture at 250 degrees C for 2 hours in master furnace. And after cooling down that room temperature, I have collected the catalyst. So then this PDK means it is palladium tetroxyl ammonium bromide, which I have synthesized by following this literature published by Radha in JAC in 2011. Um, but you can ask why 250 degrees C I have used for this synthesis. So to get the answer, I have to go to next slide. So this TOEBR, I have done the TGA of TOEBR and after making the palladium TOEBR. So we can see that the TOEBR decomposition temperature is at 210 degrees C, and 210 degrees C, and palladium TOEBR decomposition temperature is increasing to 250 degrees C because of the coordinating this TOEBR with the palladium. This decomposition temperature is increasing. So as you can see that palladium TOBR is decomposing at 250 degrees C. So if I heat the palladium TOBR at 250 degrees C, I can get only palladium, and this organic part will be decomposed or removed. So that's why I have heated 250 degrees C, and to confirm that the palladium it is fully decomposed or not, I have taken the IR of this palladium TOBR and the post-heated palladium TOBR. So these are the signature peaks of TABR at 2900 and 1500 centimeter inverse. But after heating at 250 degrees C, we cannot see those peaks. That means those are disappeared, those are decomposed. So there is only palladium. So to know that it is palladium or not, I have taken the measure by XRD, and we can see that after heating at 250 degrees C, the 600 cubic lattice structure of palladium only present there, and no organic residues are there in the sample. So after confirming this, I have loaded this palladium TeR in different weight percentage on the FeCO board and heated at 250 degrees C for 2 hours, and then characterized well with the XRD, XPS, HRTM, same and all. So this is the XRD pattern of this after heated sample. And the Miller indices written with the black colors are due to the inverse spinel structure of Fe3O4, and these blue colors are due to the palladium nanoparticles. So you cannot see this palladium peak for 2 to 5 to 8% of palladium. So because of the high dispersion of palladium over the Fe3O4, or maybe due to the narrow size of this palladium nanoparticle over the Fe3O4. But after increasing the palladium, we cannot see we can see this palladium peak. Okay, so this is maybe the detection limit of Fe3O4. So we don't know. So mostly this is due to the high dispersion of palladium over the Fe3O4. So after that, we wanted to know what is the oxidation state of palladium present in the sample. That is why we have measured the let's say photoelectron spectroscopy of the samples, and this is the palladium XPS. We can see here the two doublets of peaks are present here. The one is for palladium nanoparticle, and another one is for palladium oxide, palladium 2 plus. But this you can see this palladium oxide peak, palladium 2 plus peak is broader than the palladium 0 peak. That's why we have deconvoluted this palladium 2 peak into another into two. So another peak is due to the higher oxidation state of palladium oxide. So now how this palladium oxide is forming, how we are getting, why we are getting this palladium oxide in the sample? Because we are hitting the sample at 250 degrees C in air. So in air oxygen is there, and the surface of the palladium is capturing oxygen from the atmosphere, and that is why palladium oxide is forming. But this is not the like entire structure of palladium. It is not fully palladium oxide. It is just a surface oxidation of palladium, because we could not see any palladium oxide peak in the sample. So it is just palladium at the core, and the oxide of the palladium core is the surface of the palladium core is palladium oxide here. Okay, and then we have taken the high resolution transverse electron microscopy images, and there also we have confirmed that the palladium is present, because the lattice fringes is 0.224 nanometer is due to the palladium only. Now I'm telling that I have prepared the core shell nanosensor, but what is the proof? What is the proof of that I have prepared? It is prepared or not? So to that, to get that information, we have to take the help from this electron microscopy images, and that is why I have taken the same and stem images. So this is the scanning electron microscopy images of Fe3O4, beyond Fe3O4, and these are the palladium loaded Fe3O4. As you can see that the surface of this Fe3O4 is very smooth only for the Fe3O4, but after loading palladium, surface roughness is increasing. So this surface roughness is because of the palladium deposition over the Fe3O4. And to get the better information, we have taken the scanning transmission electron microscopy images. This is the only Fe3O4 stem images, and these are the palladium loaded Fe3O4. So as you can see, this is the the stem images we have taken in two different mode. One is the dark field, another one is the bright field, to get better resolution of the better contrast at the Fe3O4 pictures. After characterizing the catalyst, we have used that catalyst for the catalysis reaction, and first we have started with the ammonia borane hydrolysis reaction. This is the ammonia borane hydrolysis reaction graph, hydrogen generation graph, and we can see that the hydrogen generation rate is increasing with increasing the palladium loading here 10%. After that, for the 15% sample, rate is decreased. This is due to the surface area of the catalyst, because when the surface area will be more, rate will be more. When surface area is less, reaction rate will be less. Okay, this is the common catalyst common relation between the surface area and the catalysis. So why this surface area is decreasing after 10%? Because if we load the palladium beyond 10% over the Fe3O4, then the palladium nanoparticles are aggregating. When it is aggregating, surface area is decreasing, and the reaction catalytic activity also decreasing as well. So for any catalysis reaction, we have to do the recyclability, or else how do I know that catalyst is good or bad? So if the catalyst is recyclable, then the catalyst is good, and if it is not, then it is not a good catalyst. That's why I have done this recyclability of the catalyst. So here you can see that the that this rate of the reaction is increasing with increasing the number of cycle of recyclability during the recyclability, and the reason for that I will tell you in the next slide. So before that, here I want to tell you this graph is, please don't go by this the figure number like A, B and all. And then this is the hydrogen generation reaction along with the nitrophenol reduction tandem reaction. So here you can see this black color graph is for this hydrogen generation reaction in presence of water. But when I am using some nitroarene compounds, the rate of the reaction is increasing. So this is because the nitrogen compounds allow the ammonia borane to absorb on the catalyst surface. And if more ammonia borane will absorb in the on the surface, then the more hydrogen will produce at a time. More hydrogen is produced at a time, the rate of the reaction will increase. Okay. So, but the difference between 2-nitrophenol, 4-nitrophenol, and 4-nitroenolate rate is maybe due to the adjacent properties of this catalyst surface and the nitroarene compounds. And one more thing we can see that the complete production is not happening when we are using nitroarene compound. Okay, so 1 mole of ammonia borane will give you the 3 moles of hydrogen gas. And here, when you're using nitrogen compounds, then some of the gas is using for the hydrogenation reaction of nitrophenol, nitrogen compounds, and that we have calculated that the 1.6 moles of hydrogen gas needed to reduce 1 moles of nitrogen compound. And but as I told you that 1 mole of ammonia borane will give you 3 moles of hydrogen. So here only 1.6 moles is using. So where is the 1.4 moles of hydrogen gas? That gas is using for the for this the reduction of this oxide surface of Fe3O4. Okay, and this is the corresponding nitrophenol reduction graph, UV visible graph. So generally 4-nitrophenol will give you the peak at 320 nanometer, but if we add so some reducing agent, then this peak will be shifted to 400 nanometer because of the formation of 4-nitrophenolate. Uh, and in presence of catalyst, this 4-nitrophenolate peak will be increasing, and the new peak will appear at 300 nanometer. This is the formation of 4-aminophenol. So here it took only 7 minutes to complete this reaction, and then we have calculated that this reaction is following the pseudo fast order reaction. And that graph I have not shown here. And one more thing, we have calculated that the rate of the nitrophenol reduction is faster than the hydrogen generation reaction. Okay, so this is because that uh, this hydrogen is generating in this ammonia borane hydrolysis is using for two reactions here, right? One is for this it is taking water is taking that some of the hydrogen and forming hydrogen gas, and some of the hydrogen is using for this nitrophenol reduction. So when this hydrogen species is like capturing, uh, scavenging in the nitrogen compounds, then it is accelerating this hydrogen generation reaction, and that is why the rate of the reaction is more for this nitrogen reduction than the hydrogen gas generation. As I told you that the rate of the reaction is increasing if we increase the number of cycle during the recyclability study. So why is that so? Why to get that to get that why is that so? Then we start collecting the catalyst after every cycle of hydrogen generation and analyze that catalyst for with the different tools like XRT, XPS, and HRT. So as you can see that the after every cycle of hydrogen generation, the Fe3O4 peak intensity is decreasing, and one new peak is appearing at 44.7 degrees C. 44.7 degree. This is due to the iron zero nanoparticle is forming in the sample. But how this Fe3O4 is forming Fe0? I mean, what is the path of the formation of Fe0 from Fe3O4? How it is reducing? To get that answer, we check that the one very small peak is coming at 27.1 degree, and that peak is coming up to third cycle. You cannot see here because it is very less, and then it is disappearing at after fifth cycle. This peak is due to the gamma FeOOH or lepidochloride, and after third cycle, that peak is also consuming to the formation of Fe0 nanoparticle. That's why it is disappearing. This is the palladium express of the used catalyst, and we can see that the palladium 0 nanoparticle is there. Palladium 0 nanoparticle is there along with some palladium 2 plus. This is due to the palladium hydroxide formation over the palladium surface, because we have done this reaction in water. So some hydroxide, some water is still deposited over the palladium. This is why this palladium 2 plus is coming. And this is the FeXPS, RNXPS. You can see one solar peak at 6.7 electron volt along with other Fe3O4 peaks. This solar peak is due to the Fe0, iron 0 nanoparticle. And another proof of iron 0 is from HR10 images is that this the lattice fringes of 0.208 nanometer is due to the iron 0, and along with palladium lattice fringes. So that all this characterization is proven that the iron 0 is formed during the hydrogen generation reaction. So from this, sorry, take water. So all these characterization tools are proving that the iron 0 is formed during this hydrogen generation reaction, and this iron 0 is staying at the Fe3O4 Pd interface. And for any catalysis reaction, metal oxide interface is very important. If we can modify the metal oxide interface, we can change the catalytic activity. Okay, so here in our case, maybe this in situ synthesized iron 0 is have some synergistic effect with the palladium, and that is why the rate of the reaction for the hydrogen generation as well as the tandem reaction is increased. So with this, I wanted to complete my talk, and this is here is the conclusion that I have synthesized for PD coastal nanoparticles, and with the solid state synthesis process and characterized well. And then ammonia borane hydrolysis and nitrogen reduction were performed in tandem way. And, from this analysis, we could observe that this nitrogen reduction rate was faster than the hydrogen formation reaction. And during this hydrogen generation reaction, iron 0 was formed at the Fe3O4 Pd interface, and this Fe0 and nitroarene both were enhanced the hydrogen generation rate of the reaction. Thank you very much. Yes, any question I'll be happy to answer.
Yeah, I have some questions, but if anyone wants to question, can I ask? Alright.
Sweta ma'am, you can ask question, ma'am.
I don't have any question for Dino. You can ask.
That you have chosen that Fe3O4 because of this is inverse spinal or it's cost effective or what is the reason behind it?
The SHO4 is a magnetic compound, right?
Okay.
So if we deposit palladium over FeCO4 to reduce the surface energy of palladium,
Okay.
then after depositing and heat treatment and washing of the sample, we don't need to like centrifuge, or we don't need to use any say, washing process to collect the catalyst. Just put a strong magnet, you can collect the entire catalyst.
Okay.
Okay, another thing is that this Fe3O4 is a reducible support material. It can reduce in the atmosphere. So if
Yeah.
we
Okay.
and I am doing hydrogen generation reaction, so hydrogen will be there in the reaction, and that hydrogen will be used to reduce the Fe3O4 to form the Fe0, which will be helping for like enhancing the catalytic activity.
Yeah, actually means if you have iron zero, that will in presence of hydrogen, that will
I,
itself
I,
reduce the nitrogen
yes,
compound.
yes, and iron zero is very good catalyst for hydrogen
Yeah,
generation as well as
yeah, yeah.
some organic reaction also.
Yeah, means have you tried the simple alkenes for reduction?
Simple.
Alkene, alkene or alkyne, anything. It apart from
Actually, not in this study.
nitrogen,
Not in this study, I have used only cyano compound and this nitro compounds.
and probably means it's a suggestion if you wanted to take it. Means if there is hydrogen, then there we can do deep protection. In some protecting group, we can remove using hydrogen gas.
Okay.
That also I think we can check. That's all. That's all, Priya. Thank you very much, and it's a good, very good talk.
Thank you.
Dinu bro,
Yeah, tell me.
based upon that nanoparticles, it would be vary the reduction or what?
You see, like nanoparticles means you can use various nanoparticles, not only palladium. You can use different nanoparticles, but the activity will be different only, nothing else.
Okay, okay. Ultimately, we'll get the product only.
It depends on like which I mean, nanoparticles are not the selective agent, right?
Yes.
It depends on your reaction conditions and other things, but nanoparticle will just catalyst, nothing else.
Okay, okay. Thank you, bro.
Hello.
Yes.
Do you know what was the uh, part where did you struggle the most in your work?
Yeah,
I mean,
like when first I didn't know that iron zero is forming in my sample, so I didn't know that I thought this is just a simple straightforward catalysis work. Then it came to my mind that after the catalysis reaction, I have to do some characterization. Then I found that some peak is coming in the XRT. But that time I didn't know that peak is because of iron zero. So I had to find that what is that peak, and then I came to know that this is iron zero. And this is very surprising also. And one more thing is that generally you can see this palladium XPS here. Yeah, this palladium XPS, the second row middle graph. So here I didn't know that we can complete this palladium into like four peaks. One of my reviewers for this work suggested that palladium XPS was not characterized well. So then I had to find that what is the other characterization I can do with the palladium. Then I came to know that we can feed the palladium peak with 4 5 peaks. Then so this is also very like very learning tool for me from this reviewer comments. So these are the some difficulties I have faced during this work.
okay.
Yeah.
Dinu, now I have a question.
Yes, ma'am.
So, do the activity depends upon the size and the morphology of your particle, or it is independent?
It is dependent on the size of the nanoparticles, and it is dependent on the support materials also. Like if your particle size is less, the activity will get, because we know that nanoparticle size is less, than activity will be more because of the surface area to volume ratio will be more. And if
So,
more
what was your size?
my particle size was like for it was actually this palladium is not a completely spherical all over the Fe3O4. It is two different types of palladium is there. One is thin layer, one thin complete atomic layer of palladium, and one is the ball kind of thing of palladium. Because these balls are forming because to reduce the surface energy of these palladium atoms. So when to reduce the surface energy, they are trying to form a ball. That's why we are saying the ball, and the ball size is 5 nanometer only.
Okay.
And this thin layer
They
of
don't aggregate. They don't aggregate.
it is aggregating when I'm depositing the pellet beyond the 10%. You can see here
Hmm.
in this once again. You can see here for this is black is for 2% palladium, red is
Uh-huh.
there is 5 blue is 10 and 15 is the this magenta color. So
Mm-hmm.
we can see the trend that with increasing the palladium rate is increasing, right? But why
Yes.
the 15 rate is decreasing? This is due to
Okay. Yeah.
Ma'am, you want to ask anything, ma'am?
Done. Done.
Thank you so much, Dinu. Thank you.
yeah, thank you.